Okay, good morning to everybody, and thank you for attending the last lesson of this course on analytical techniques for wave phenomena. In this last lesson, I will address topics concerning scattering, electromagnetic scattering from spheres that we started considering in the previous lesson. And today, my topic will be mainly devoted to plane wave scattering by spheres. And to start with, I will consider the simplest case. Let me admit also Dr. Fuscaldo. I wish to mention that this lesson will be followed, as is tradition in this course, by a conclusive seminar, a very interesting one that will be given by a colleague of mine, Dr. Walter Fuscaldo, who is now attending this lesson. So stay tuned if you have the possibility of continuing after the end of my lesson, because it's a very interesting contribution to this course. So coming back to the lesson, let me enlarge the screen. What I will try to describe you is how to treat the problem of a uniform plane wave that is impinging on a perfectly conducting sphere. As you can see in this figure, the wave is a uniform plane wave that propagates in free space with a wave number k. It propagates along the z-axis, and I will assume that without loss of generality, its electric field is polarized along the x-axis. So its expression in spherical coordinates for the electric and magnetic fields, which are purely transverse with respect to the z-axis of propagation, is given by these two very simple expressions. The dependence on the spherical coordinate is via two simple exponential functions. And in the exponent, you will find the radial coordinate r and the cosine of the angular coordinate theta. Now, since we wish to employ to enforce boundary conditions on the surface of this sphere, the geometry says that it is convenient to work with fields that are transverse magnetic or transverse electric with respect to the radial direction. So our first task is that of representing this incident field as the sum of a TM field and a TE field with respect to the radial direction. And to do so, let us focus on the radial component of the electric field, which is given, as you can see here on top, by the x component, that is the total electric field, multiplied by the cosine of phi and the sine of phi. Now, why are we focusing on the r component of the electric field? That is because the r component of the electric field is for sure a purely TM component. That's because simply the transverse electric field, by definition, has a zero component in the radial direction for its electric field. So when dealing with this component of the electric field, we are sorting out a purely TM part of the field. Now, it's easy to see that if you multiply the exponential function I described before times the sine function, what you get is the angular derivative with respect to theta of the exponential function itself. And now, the latter exponential function can be expressed in terms of spherical waves, as we showed in our last lesson. That is, as an infinite summation of some numerical factors times a spherical wave function, j sub n is the order that goes from 0 to infinity, times a Legendre polynomial, this p function with the index n, whose argument is the cosine of theta. If you perform this angular derivative in terms of the argument of this Legendre polynomial, that is, if you differentiate with respect to the cosine of theta, the factor minus sine theta comes out, and finally the part of this formula that is highlighted in green can be shown by the formula reported at the bottom of this slide to be writable as a Legendre function of order n and superscript 1, so associated Legendre function with two indices. So this is the final form for the radial component of the electric field. Now, since, as I said, the radial component is purely Tm, we wish to derive this radial component in terms of a magnetic potential, a radially directed magnetic potential, which is a Debye potential, as we saw in the previous lesson, whose form is again that of an infinite summation of spherical functions, whose general term contains a still unknown coefficient, a sub n, that now we wish to determine. In order to determine these unknown coefficients, a sub n, we may recall the link between the potentials and the fields. In particular, the radial electric field is given by this expression in terms of the radial vector magnetic potential, and by also taking into account that the spherical modified Bessel functions j hat satisfy this ordinary differential equation. Finally, by operating on the above expression for the potential, you are able to derive the bottom expression for the radial incident electric field, which can now be compared with the expression we derived in the previous slide. It has exactly the same form, but now here we see the appearance of these coefficients a sub n. So by equating this expression with the previous one, here, we are able to determine the value, the exact values of the unknown coefficients. And this expression, the expression is reported here in the box. It's a very simple ratio between numerical constants that depend on the order n. By using exactly the same procedure, by duality, starting now from the radial magnetic field and considering now a radially directed electric potential, we are able to reach the same result for the electric potential, and we will find exactly the same coefficients as those we have already found for the magnetic potential. So this completes the derivation of the splitting better of the incident field into two separate Tm and Te parts described by magnetic and electric potentials, respectively. Once we have these, it's easy to enforce boundary conditions separately onto the Tm and Te parts, and the boundary conditions require the introduction of scattered potentials, because there will be a scattered field. The expression for the scattered potential will be formally the same as that for the incident potential, with the only difference that now the radial function will not be a Bessel function, which is a standing wave solution, regular everywhere, but rather a Hankel function, which represents a traveling wave dependence on the radial coordinate with an outgoing character, since we are using the second kind Hankel function. So if you sum the incident and total and scattered potentials, you will find the total potentials, in which you can see inside the brackets the occurrence of the incident field through the J functions and that of the scattered field through the H functions. In addition, we have this pair of infinite unknown coefficients, B sub n and C sub n, which can be found by enforcing the boundary conditions, that is, the vanishing of the total tangential component of the electric field on the surface r equal a radius of the sphere. If you do so, you will find very simple expressions for these unknown coefficients that describe the scattered field, B sub n and C sub n. They are simple ratios of the Bessel function J, of its derivative, with respect to the derivative of the Hankel function in the denominator. Okay, once you know this procedure, you can apply it also on different kind of sphere. For example, a penetrable one, a transparent sphere. For instance, if you have a homogeneous isotropic sphere with constitutive parameters epsilon d and epsilon and mu d, you will follow exactly the same pattern. In addition to the scattered field outside the sphere, however, there will also be a transmitted field that exists inside the sphere, which is now penetrable. And this can be expressed again in terms of electric, magnetic, or electric potentials, in which the expression is exactly the same as that of the incident field, but now with different coefficients, d sub n and e sub n. Note that now the wave number that occurs inside the Bessel function argument is the wave number kd of the medium inside the sphere, of course. since we are describing a field that is a solution of Maxwell equations inside that medium. By enforcing the boundary conditions, which are now the continuity of the tangential components of both the electric and the magnetic fields on the surface of the sphere, you may find a system of linear equations in the unknown B sub n, C sub n, D sub n, and E sub n. And finally, you are able to find everything, the scattered as well as the transmitted field. For example, if you are interested in the scattered field, what you need is the expression for the coefficients B sub n and C sub n, and those are a little more complicated than those very simple that we found for the perfectly conducting case. They are, again, ratios of linear combinations of spherical Bessel functions and spherical Hankel functions, in which you can, of course, recover the perfectly conducting case as a limiting case, in which you let the permeability of the sphere go to 0, and simultaneously you let the electric permittivity go to infinity, such that the wave number remains finite. Okay, having said that, we know everything, so the scattered field can be analyzed, and for instance, we may study the scattered field very far from the sphere, so the far scattered field. To do so, we need to consider the asymptotic behavior of the functions that express the radial dependence of the scattered field, in particular of this modified spherical Hankel function h, which in the asymptotic limit when r, the radial distance, is very large with respect to wavelength, and so kr is a very large number, a dimensional number, can be represented by this expression, j to the power n plus 1 times e to minus j kr, which says that this wave is traveling towards infinity. Now, in addition, if we retain only the dominant asymptotic terms of the fields, which are those that depend on r as the inverse of r, so those that depend inversely on the distance from the center of the sphere, the final result for the two far components of the field is that E theta and E phi can be expressed by the two equations in the box, where you can see the radial dependence is expressed by the usual form that you find also in the free space Green's function, so e to minus j kr divided by r. Then there is the amplitude of the incident field, of course, since the problem is linear, the amplitude of the scattered field will be proportional to that of the incident field. And the dependence on the wave number k, as well as on the radius of the sphere, is contained inside this adimensional parameter beta, which is the first argument of these two functions, S1 and S2. The latter functions depend only on theta, so the angular behavior of the scattered field depends on these two important functions, the so-called amplitude functions for the sphere scattering, whose expression is reported here. This is given by an infinite summation, and inside these infinite summations, you can find the coefficients B sub n and C sub n that we found by enforcing the boundary conditions on the surface of the sphere. This form of the solution was obtained initially by Gustav Mie at the beginning of the 20th century, when this German scientist was studying the properties of optical scattering by dispersions of very, very small particles, in particular metal particles, inside a liquid. So he studied, for instance, gold colloidal solutions. And this was the first time that an explicit expression for the scattered field by a sphere was given in an exact form. An alternative expression for the same Mie series can be found here, in which the same functions are expressed in terms of these angular factors, P sub n and T sub n, and in which I have now indicated with these coefficients S1 and S2 the dependence on beta, which is the normalized radius of the sphere, and these coefficients for a dielectric sphere are reported here. They are given in terms of the dielectric constant of the sphere, which is given by the permittivity of the vacuum multiplied by the square of the refractive index, n, assuming that the sphere is non-magnetic. And so in this case, the explicit expression for these coefficients is the one reported in this slide, where the symbol ln with an apex indicates a logarithmic derivative, which is defined as the derivative of the logarithm of its argument. And you can verify, that's an algebraic exercise, that this alternative form for the Mie series is equivalent to the original one. Once you have the Mie series representation for the scattered field, you can evaluate interesting things, like, for example, the backscattered field from a perfectly conducting sphere. So you can calculate the backscattering cross-section, also known in the radar realm as the echo area of this scatterer. This is defined by this limit of the ratio between the squared amplitudes of the scattered and incident fields multiplied by r squared. And by employing the Mie series, you will find a quite compact expression for the echo area, which is reported here below. And if you plot the echo area normalized to squared wavelength in free space in the vertical axis as a function of the normalized radius of the sphere, the radius is normalized with respect to the wavelength lambda, you will find this curve, a behavior like this, in which you can see a generally increasing trend of the echo area, however, with oscillations, and you can distinguish a first range in which the radius of the sphere is very small with respect to the wavelength, and this is the so-called Rayleigh range, in which the echo area basically scales as the inverse fourth power of lambda. And this is a peculiar behavior of scattering when you are considering small scatterers, and this is the reason why we see blue, the sky. That's basically because scattering of the sunlight that occurs inside the sky is enhanced for small wavelengths because of this law of scaling, like the inverse fourth power of wavelength, and so therefore blue light is scattered more efficiently than red light in the electromagnetic spectrum of visible light. In the opposite limit, when the sphere is becoming very large, we have the optical limit, in which basically the echo area tends to the physical cross-sectional area, pi times the square of the radius, and the optical limit is reported here with a dashed line. As you can see, in the intermediate range, which is also known as a resonance range, you will find many oscillations that tend to become more and more rapid and diminish in their amplitude around the optical limit. Now, having said what is the formal solution of scattering, as we said in the previous lesson, the Mie series, also known as partial wave expansion, is an exact solution. However, it is quite inconvenient if you are considering very large scatterers, because you need to sum a very large number of terms to achieve an acceptable accuracy. So, last lesson we saw some techniques to improve the convergence of the Mie series, basically the Watson transform. I will mention you now how, also employing those techniques and other asymptotic techniques, it is possible to achieve an asymptotic high-frequency representation of the field scattered by a sphere. And to do so, we will introduce the so-called localization principle, which holds in the asymptotic limit when the radius of the sphere is very large in terms of wavelength. And so the adimensional parameter beta, which is defined by the product k times a, is a very large number, that is, it's much larger than unity. As you can see here, in this limit, I have reported again the configuration, the incident plane wave, that is its wavefronts, which are perpendicular to the z-axis, which is the propagation axis, may be thought to consists of the union of separate rays. So we are describing the incident field in terms of ray optics. And each of those rays basically has its own propagation path independent of the other ones. So basically the wave is localized around those rays, and that's the physical essence of the localization principle. Of course, this is an approximation, as always in the case of ray optics. Consider, for example, an entire planar wavefront, as here reported in purple. If you consider a small portion of this wide wavefront, this may be thought to define a ray tube, that is a bunch of rays, and this ray tube, for some length during the propagation of the wavefront, can be described as if it had its own existence, that is, as if it propagated independently of the entire wavefront, at least until the rays that make the ray tube start to diverge. So there will be a distance up to which the rays more or less propagate linearly and parallel one to each other. After this distance, which is of the order of d squared over lambda, where d is the extent of the portion of the wavefront we are considering, the rays start to diverge angularly, and this is the classical beam spreading that is due to diffraction. That's a typical effect in free space propagation of any optical or, more generally, wave field. Note that this range, d squared over lambda, is almost the same as the Rayleigh range, for example, in Gaussian beams, if you are familiar with them. And it's also related to the far field distance, that is the distance which defines the Fraunhofer region related to the source constituted by this portion of the wavefront. Now, an asymptotic analysis of any term of the infinite Miri series shows that this term will give rise to a single ray that passes at a certain distance from the origin, as you can see here in this drawing. The distance from the origin of this ray is known in the literature as the impact parameter. Let me admit your colleague, one moment. Okay, here we are. The impact parameter, there is one for each of the Mie series terms, will depend on the index n, and so it's growing with n. For small values of n, the rays will pass close to the origin of the sphere, whereas by increasing n, the rays will be farther and farther displaced from the origin of the sphere up to a point when they do not hit anymore the sphere. So in particular, it's easy to see that if the order n is such that n plus 1/2 is less than beta, which is the adimensional radius of the sphere, then the rays hit the sphere, and the spherical Bessel functions that make up the Mie series have an oscillating behavior as a function of n. Whereas when the rays do not hit the sphere, so their index is so large that n plus 1/2 is larger than beta, the behavior of these same Bessel functions is exponentially decreasing as a function of n minus beta, and therefore their contribution is less and less important. So basically, the most important terms of the ray series, of the Mie series, are those that correspond to rays that physically impact on the sphere, as one would expect on a physical ground. Now, as we saw in the previous lesson, the Mie series, the partial wave expansion, is not convenient because you need to sum a huge number of terms. However, by employing the residue theorem in a sort of reverse fashion, you can represent the same series as a contour integral, for example, the one that is represented here in this complex plane of the S variable, which is known as the complex angular momentum variable. And now, once you have an integral representation for the field, you can either deform the contour to achieve an alternative representation, for example, in terms of another family of poles, which will hopefully provide you with a more rapidly convergent series, or in any case, as we will do now, you can look for a high-frequency asymptotic evaluation by deforming the integration path, for example, onto a steepest descent path that passes through some saddle point, and in doing so, you will encounter some critical points, such as the already mentioned saddle point, or maybe pole singularities, which will give you some important physical contribution. In particular, let us see the results. I will not show you the analysis, but I will give you only the final results of this analysis. Any real saddle point, let's call it S over bar, which is located within the range between 0 and beta, will correspond to a ray optical, a geometrical optics ray that hits the sphere at the impact parameter given by the ratio between the saddle point and the wave number k, as you can see here in the box. So we have a ray that impinges on the sphere and will be scattered. Consider that now we are treating a perfectly conducting sphere, so there is no field transmitted inside, but only an incident and the scattered field outside the sphere. In addition to saddle points, there are complex poles that can be captured, and these complex poles, that are also known as edge poles, will correspond to creeping waves, that is, waves that penetrate the shadow region and that propagate tangentially with respect to the sphere surface, and they account in a very convenient and rapidly convergent representation what is happening inside the deep shadow region. This is so because the imaginary part of these complex poles determine a damping of the wave, and this damping is more and more pronounced as you go deeper and deeper into the shadow. So if you are in the deep shadow, the series will be made by rapidly converging terms that are exponentially going to 0. And so you need just a few number of terms to accurately account for the field in the shadow. The intermediate region between the lit part of the sphere and the shadow part of the sphere is the so-called Fock region, because it was first studied by the Soviet scientist Fock in the 40s. And that's a sort of transition region from the lit region in which you have a real saddle point that corresponds to the incident ray, and the shadow region in which you have no real saddle points because you have no rays, and instead you have complex poles. This is the so-called penumbra in Latin. Now, it turned out that this representation, based on the Watson transformation, was not the most convenient. In particular, an alternative to the Watson transformation, a modified form of the Watson transformation, was introduced in the 60s of the last century by this Brazilian physicist, Henry Moises Nussensweig, who studied scattering from spheres, and he started with perfectly conducting spheres, by basing his analysis on the so-called Poisson sum formula, which expresses a general sum, like the one you can see here on the left-hand side of this equation, in terms of a modified sum, in which you sum now terms which are basically the Fourier transforms of the original functions in the left-hand side summation. The Poisson sum formula is known for being able to convert a slowly converging summation into a rapidly converging summation. In our case, what we need is, again, an interpolating function that reduces to the discrete addends that occur in the original summation, and that is a function of the complex variable lambda. Now, it is possible to extend the integral over the complex variable lambda to an integral that is made on the entire real axis, and then once you are there, you can deform the contour, as we already described, in order to achieve an asymptotic analysis through the steepest descent method. In contrast with the standard Watson procedure, this modified procedure based on Poisson sum formula is able to give you an acceptable result in all the angular regions around the sphere, and so it's more complete. And it can also be used to consider high-frequency scattering from a dielectric sphere, which is a much more complicated problem, because now, if the sphere is penetrable, the waves are able to get inside the sphere, and this leads to some resonance effects, which have a much weaker damping with respect to the resonance effects that would occur in a perfectly conducting sphere. In analytical terms, this is equivalent to saying that there are many complex Regge poles that are located close to the real axis. So they are complex poles, but their imaginary part is It's very small. And since it is very small, the relevant series that is obtained by employing the standard Watson transformation would be not a rapidly converging one. So there would be no convenience in employing these Watson transformed series. In order to recover a fast converging series, it is necessary to modify the form of the solution by rewriting it in terms of surface interactions, much in the same way it is done in the treatment of, for instance, Fabry-Perot interferometers in terms of a multiple reflection description, which is recalled here in this slide on the left. You know, the Fabry-Perot interferometer is based on a plane parallel cavity. So there is a ray that impinges from the left. This ray enters the cavity and starts bouncing back and forth. Each time it produces an exit ray, and there will be a system of infinite exit rays that are summed coherently on the exit side to produce the transmitted field. Now, if you represent the transmitted field in terms of an infinite summation of rays, as is done in this picture, you are basically describing each scattering interaction on a local basis as a surface interaction that is between a ray and a single planar interface at a time. The left interface of so the left mirror of the cavity or the right mirror. Something similar can be done. A sphere can be considered as a resonator in which the waves bounce back and forth between the center, where perfect reflection occurs, and the surface of the physical sphere, where the surface interaction is described by the spherical Fresnel coefficients. That is a modification of the ordinary Fresnel coefficients that takes into account the curvature of the sphere. And therefore, here we have reflection as well as refraction or transmission outside. If you do so, you will be able to express the amplitude coefficients of the Mie series, these S functions on the left-hand side of this equation, in terms of spherical reflection and transmission coefficients between the region inside the sphere, here labeled as region 1, and the region outside the sphere, which is here labeled as region 2. As you can see here, you can find the reflection coefficients R, the spherical reflection coefficients R, and the spherical transmission coefficients T. If you employ this form of the amplitude coefficients S, you are working in the same way as Peter Debye worked in his seminal paper, appeared in the 20s of the 19th century, and this expansion is therefore known as the Debye expansion. To this expansion, you can apply the techniques based on Watson transformation and asymptotic analysis. In particular, the scattering amplitudes are expressed as the sum of a direct reflection from the surface, and then a sum of a theoretically infinite number of terms, these here are highlighted in red, each of which expresses transmission after a certain number, p-1, of internal reflections. So if you apply the modified Watson transformation to each of these terms in the Debye expansion, then what you will obtain is a series of complex poles that are now different from the previous ones, and they are named Regge-Debye poles, whose imaginary part is now not small anymore, it's large, and so it's associated with rapidly damped creeping waves, and therefore the resulting series will be rapidly convergent. So you are able to achieve a rapidly convergent asymptotic expansion of the overall scattered as well as transmitted field. So the result, again summarized here, is the following. If you have a real saddle point, again S over bar in the range between 0 and beta, now for the pth Debye term, and since we now have an infinite number of Debye terms, then this saddle point will correspond to a ray that hits the sphere at the impact parameter indicated here with the letter Q, again S over bar divided by K. Now this ray undergoes, however, p-1 internal reflections, where p is the order of the Debye term, as you can see in this drawing, in which the case a case with p=3 is shown. Q is the impact parameter, so the distance between the incident ray and the axis of the sphere, the origin. Here you can see the ray enters the sphere. It is partially reflected inside in this point. It is again partially reflected inside in this other point, and finally it exits there. Of course, you could follow more internal reflections, and those would correspond to higher order Debye terms. Now, the meaning of complex poles, the Regge Debye poles, again, is that of introducing creeping waves excited this time by tangentially incident rays. However, in contrast with the perfectly conducting sphere, these waves now not only travel around the surface of the sphere and they shed diffracted rays, so they attenuate during the propagation because of this, but they are also able to undergo critical refraction inside the sphere, as you can see here. Theta sub c is the critical angle for refraction. So they are able to penetrate the sphere and, in a sense, take some shortcut through the sphere. So, for example, in this drawing, I have considered the case with p=2, so a single internal reflection. And there are two shortcuts taken in this example, and then that's the exit ray, which the exit ray is again tangential with respect to the sphere. Now, if you consider all the rays that are incident on the sphere, you will find that depending on the angle, different phenomena may occur. For example, there are transition regions that are that occur between the lit and the shadow parts, angular regions. And this is a standard, common transition region in which you have the disappearance of a real ray, because a real ray is present on the lit side, but it is not present anymore in the shadow side. And analytically, this means that a saddle point is replaced by a set of Regge Debye poles. So instead of having an incident ray, you have a set of creeping waves, and with a transition region of the Fock type, exactly as for the perfectly conducting spheres. But in addition to that, many other interesting phenomena occur for the case of a penetrable sphere, because, for example, another kind of different transition region occurs near the angles for which the scattering angle goes through an extremum, if you consider the scattering angle as a function of the impact parameter. And this is the case of the rainbow, as we will now see more in detail. And finally, another less well-known phenomenon is that of the optical glory, which occurs in the backscattering region, so close to the direction from which the waves are incident upon the sphere. And this is, again, related to complicated interactions between rays and transition regions. So in the last part of this talk, I will address in a more qualitative way, descriptive way, these two beautiful optical phenomena, that is the rainbow first, and then the optical glory. And let me start with the rainbow. Here you can see a beautiful photo of a double rainbow that was taken in British Columbia. If you observe the photo with attention, you will see that there is a bright inner band, colored band, which is the so-called primary bow, with the red color on the outside and the violet on the inside. Then there is a secondary bow that is also quite clearly visible with a larger radius somewhere here, in which the order of colors is reversed. So the red is in the inside and the violet is in the outside. Inside the two bows, the primary and the secondary ones, there is a region of the sky which is considerably darker than, for example, the region inside the primary bow, and that's the so-called Alexander's dark band. And furthermore, it is also possible to observe on the inner side of the primary bow some faint stripes of pink and green, and they are the so-called supernumerary arcs. They are a bit on the inner side of the violet color of the primary bow. Now, the geometry of the rainbow was studied since many centuries ago. For example, the angle of the primary and secondary bow was first measured in 12 in 1266 by Roger Bacon. And basically, the geometry of the rainbow is determined by the way each of the small particles, the small droplets of water dispersed in the atmosphere, scatter the incident sunlight. That's because the total angle, the scattering angle, which is the total angle through which a ray of sunlight is bent by its passage through a raindrop, depends on the impact parameter, and in particular, one may say that rays are strongly scattered at angles close to 138 degrees and 130 degrees, and those give rise respectively to the primary and the secondary rainbows. Between these angles, there is the Alexander's dark band, and since the refraction phenomenon is dispersive, that's because of the dispersive nature of water, of raindrops, basically the angle of maximum scattering depends slightly on frequency, or if you prefer, on wavelength. So since the sunlight is white, so there are all the colors inside it, but each color will be deflected with a maximum scattering angle slightly different from the others. The final result is that we observe a rainbow not exactly with a single angle, but with a range of angles which corresponds to the different colors. Here you can see what happens exactly when a ray impinges onto a water droplet. Consider a single incident ray coming onto the droplet with a certain impact parameter. This ray, for example, is directly reflected from the raindrop, and so it does not enter partially. And this ray that it does not enter the droplet is classified as a class 1 ray. However, if you follow instead the refracted ray that enters the droplet, you have a second surface interaction here. The ray that goes outside the droplet now at this point are class 2 rays. Whereas if you still remain inside, you have a third point of interaction. And now the rays that are refracted here are the class 3 rays, and these give rise to the primary rainbow. If you still go on in the fourth surface interaction point, originate the class 4 rays, which give rise to the secondary rainbow, and you could go on, so to considering rays of higher classes, which give rise, each of which give rise to higher order rainbows. Now, consider that for rays of each class, only a single factor determines the value of the scattering angle, which is the angle of the exit ray, and that factor is the impact parameter. So how far is the incident ray from the axis of the sphere? So if you study the dependence on the scattering angle on the impact parameter, you will be able to predict the rainbow angles. This is done in this figure, in which you can see in the upper red curve the dependence of the scattering angle for class 3 rays as a function of the impact parameter on the horizontal axis. You will see that this curve has a minimum, and the minimum occurs at the impact parameter B here, that gives rise to the scattering angle equivalent to the angle of the primary rainbow. Whereas if you consider class 4 rays, you will see that the curve is the red one here below, and it has instead a maximum that corresponds to the secondary rainbow ray. There are no scattered rays inside the minima and maxima. So here you see the Alexander's dark band, in which up to this order of approximation there would not be exit light, whereas of course there are higher order rays that account for some light inside this band. Here is a representation of what happens if you vary the impact parameter. Here you can see a single ray in red, along with a family of parallel rays that impinge on the sphere. And if you follow the refraction and reflection of these rays inside the droplet, you will find that there is the formation of caustics. And as we saw in one of the first lessons of this course, in the vicinity of the caustics, the ray optical field diverges, and in practice, the actual optical field has a local maximum of its intensity. They are also known as Barning curves for this reason. As we saw, the caustics are the envelopes of a family of rays. And here you can see the real caustic that is formed by the rainbow ray, which is the ray which exits with the largest or the smallest, depending on the order of the rainbow, exit angle or scattering angle. It's interesting that in the 19th century, a quantitative theory of the rainbow was attempted by the astronomer George Airy on the basis of this ray optics description. However, in addition to drawing the rays and the caustics, what Airy did was to consider an initial wavefront that is by definition orthogonal to each ray in the considered family of rays. And by guessing actually the amplitude of the wave function onto this initial wavefront and using the standard radiation integral, George Airy was able to, for the first time, account for many of the characteristics of the rainbow that were not explained by the already existing theories. In particular, consider, for example, the polarization of the rainbow. He noticed that the internal angle of refraction for the rays that constitute the main rainbow, by sort of chance, fall in an angular region very close to the Brewster angle. So therefore, the radiation that is capable of forming the primary rainbow has lost most of its parallel polarization. That's because at the Brewster angle, when you have internal refraction, at the Brewster angle, there is no reflection, but total transmission. So basically, if you observe light in the primary rainbow, you will find that it is strongly polarized perpendicularly, okay, to the incident plane. This was first observed by Biot and Brewster. In this plot, you can see the prediction about the rainbow of 3 early rainbow theories. The oldest one, which is due to Descartes, is a purely geometrical description based on ray optics, and the geometrical theory of Descartes is reported here with the red curve. It would predict an infinite amplitude of the scattered field close to the rainbow angle, and nothing in the dark band, so complete shadow before the rainbow angle, and a monotonically decreasing amplitude for angles above the rainbow angle. This was improved by Thomas Young, which for the first time introduced interference in his theory, and by doing so, he was able to derive a non-monotonical decrease of the amplitude, as you can see here in the gray curve, in which to a first decrease there follows a number of oscillations, so minima and maxima, okay, and the first secondary maximum would be the first supernumerary arc of the rainbow. Finally, Airy theory is better because he was able to account for the non-zero intensity, which occurs in practice before the rainbow angle, so in the dark band. And furthermore, by considering diffraction, as I described before, he was able to relocate the minima and maxima, and in this relocation, it was closer to the actual experimental observations. But even better than the Airy theory, which for a century or so was the best available theory, the complex angular momentum approach that is based on the modified Watson transformation that I was mentioning before, was introduced by Nuss and Zweig in the 60s in order to overcome the strong limitations of the validity of the Airy theory, which is accurate only for very restricted angular ranges close to the rainbow angle and only for very, very large droplets, so for beta larger than, say, 5,000. In the complex angular momentum theory of the rainbow, it is possible to perform a more refined asymptotic analysis in which you will see that the rainbow is originated by 2 coalescing real saddle points that after coalescing become 2 complex saddle points. And by doing so, if you perform all the necessary and quite complicated calculations, you will find a result which is like this, in which you can see the exact solution with the light gray curve, which is the most oscillating one, which is quite well represented by the result in red, which is the complex angular momentum theory, and in which you can see also the comparison with the area theory, which is basically quite far from the exact results, especially for large scattering angles. So even though the main scattering angle maximum is more or less right, the supernumerary arcs are not well described by the area theory, because when the area theory has maxima, the actual curve has rather minima, local minima, as you can see from this curve. Okay, this is to say again, and that's the leitmotif of this course, that by working in the complex domain and performing refined asymptotic analysis, you get more refined results and also more physical insight into what's happening in your phenomenon. Finally, I will show you what's another beautiful optical phenomenon, which is the so-called optical glory, which was for the same time reported in the 18th century by a French scientific expedition that was sent on the top of a mountain, a very high mountain in what is now Ecuador. And here you can see the words that were written in their diary by these reporters. As you can see, they were in at a high altitude on a mountain. There was a cloud. The weather was very cloudy. However, a cloud that was covering them suddenly dissolved, and so the rays of sunlight could come through, and they projected a shadow. For example, here you can see the shadow of a man, of a human, onto the clouds that were in front of this subject. And then each as you can see in their words, each of us saw his shadow projected upon the cloud. And what was most remarkable is that the appearance of a halo or glory around the head, here you can see this sort of colored circle, like a circular rainbow, but different from circular rainbow. And the most surprising thing was that of the 6 or 7 people who were present, each of them saw the phenomenon only around the shadow of his own head, and saw nothing around other people's heads. So this is probably historically one of the phenomena that gave rise to the representation of saints in iconographic fine arts in order to identify them as very special people. You can also observe glories if you are on an airplane, if you are lucky, if you are close to a glass window, because if you see the shadow of the airplane projected onto a cloud, and if you are observing things in the direction opposite to the sun, you will be able to see the very same phenomenon, that is this circular colored ring around the center of the shadow. Now, since glory is made of light that bounces back nearly in the same direction from which the incident ray comes from, it requires a quite particular alignment between the sun, the observer, and the cloud. So it is a very rare phenomenon. And that's also why you can always observe it around the shadow. That's because it's basically a backscattering phenomenon. So the different colors of the spectrum, again, due to the dispersion in the water droplets in the atmosphere, they are scattered at slightly different angles. And for the same reason I explained before in connection with the rainbow, what you observe is not a single bright white halo, but rather a set of concentric rings having different colors. So an iridescent pattern. One of the first attempts at explaining this phenomenon was, as reported here in this picture, a simple geometrical optic model in which you would have an incident light ray that enters the water droplets, is backscattered the other side and then exits in the exact backscattering direction, thus forming an enhanced scattering to the eye of the observer. Now, unfortunately, due to the value of the refractive index of water, you may verify that it is actually not possible to find a single incident ray that produces something like the thing that is described in this figure, because basically there will be no ray that is scattered back in exactly the same incident direction. In particular, there will be a minimum gap of 14 degrees between the direction of the incident ray and that of the backscattered rays. So in the 50s of the last century, Van der Hulst, a Dutch scientist, suggested that maybe surface wave had a role in this phenomenon, and in particular that it was possible that electromagnetic surface waves were excited temporarily, and they would therefore propagate along the surface of the sphere in the form of creeping waves in order to compensate for this gap that would be needed in order to cover it, in order to achieve a light scattered in exactly the same direction as the incident ray. As you can see in this exaggerated figure, in which you can see there is a small portion of this path that is covered in a curved fashion in red by these creeping rays. And then again, there is internal refraction, and then internal reflection, and finally, reciprocally, again, the conversion of an internal field into a creeping wave, and finally, the emission of a tangential scattered ray. Now, a refined analysis shows that this effect actually takes place. However, it is not sufficient at all to give a quantitative explanation of the intensity of the phenomenon in the backscattering direction. So it gives only a minor contribution to the energy that is contained inside the halo that you observe in a glory. Again, complex analysis comes into play because Nussenzweig was able to show with an asymptotic analysis based on the approach that I described before, that the phenomenon is very complicated and it has many aspects. However, most of the light that you can see in an optical glory is actually the result of tunneling, wave tunneling, because it originates from rays that do not exactly hit the droplet. They come quite close to it, but they are outside it. And then there is, therefore, tunneling, like the one you can see in optical, the phenomenon of optical frustrated internal reflection. This tunneling, which occurs via evanescent waves, so again, complex waves, is able to let some power enter the droplet. And once it's inside the droplet, this power, this incident ray, starts bouncing inside, thus forming a resonant pattern. And that's a sort of optical resonance. This is called also mirror resonance, and that's resonance in which most of the field remains confined inside the droplet, close to it, and sometimes it exits, thus forming, in particular in the backscattering direction, the halo that is the representation of the optical appearance of a glory, in much the same way as it occurs in annular ring resonators. In that case, the resonant phenomenon is called a whispering gallery mode, because the same kind of phenomenon occurs in acoustics, in particular in indoor ambience with a particular shape in which the voice, so an acoustic wave, can reach very distant points by propagating close to the boundaries, the curved boundaries of the room. Okay, I think that I've said more or less I wanted to say in this course. So this is the epilogue that you can read by itself. I would like to thank you very much for having had the patience of attending my lessons. I hope you enjoyed them. I will post the PDFs of these last two lessons in a few minutes on the website of the course, on the e-learning website of the course. Here you can find also the bibliographic references that are relevant to the topic of scattering by spheres, and which is made mostly of the papers, the beautiful papers by Nussenzweig. And finally, I would like to introduce you, our guest, who will conclude this course, and as I was mentioning you before, is Dr. Walter Fuscaldo, who should be with us. If yes, I can see him. He is connected.
Paolo,
and
scusa, noi
sì,
ti lasciamo.
Grazie.
E volevo dirti che in tutta la prima parte c'era una stranissima voce di fondo che si sentiva,
Sì.
anche se sembrava che tutti i microfoni fossero spenti, però non si capisce perché.
Poi te la spiego,
Poi
c'è una spiegazione molto semplice. Sì.
Non ti preoccupare.
Vabbè. Grazie a tutti per l'attenzione dal corso di Microwaves.
Ma non riusciamo a seguire. Ciao.
E aspetta che non lo sento. Walter, ci sente? Un momento che lo vado a intercettare fisicamente e sono subito da voi. Okay, 1 minute and he will be with us. Okay, here we are. Actually, Dr. Fuscaldo will connect from my PC, so I have the pleasure of introducing him to you. Dr. Fuscaldo graduated from Sapienza University. He was a student of Professor Galli, and he was also a PhD student here. He started his research and who is now and is now at the National Research Council here in Rome. He started a brilliant career in research. He studied many different topics, starting from leaky waves up to special materials and many other interesting things. And it is a tradition of this course that a final seminar given by him concludes the course. So I really thank him for his availability. The subject of the course is a very interesting one, and with many subtle and explicit connections with the contents of the present course. I hope we will enjoy it, and I leave the connection to Dr. Fuscaldo, who will employ his own headphones, I guess.
No, we can't able to hear you. Nothing.
Okay. Excuse me, we have a small technical issue. Dr. Fuscaldo will try to connect with his own laptop to this call, and let's see if he manages. One moment of patience. A questo punto ti puoi appoggiare pure là, se vuoi, da Alessandro, forse sei più comodo.
Can you hear me? Can you hear me?
No, in effetti no.
Ti posso chiedere?
Le cuffie vuoi?
Io ti sento.
Sì. Tu mi senti perché ho...
Sì, no. Aspetta un attimo, fammi provare. No, qui non c'ho manco. Vado a vedere un altro paio di luci. Can you hear me? Si sente? Okay, so now you can hear me okay, right?
Yes.
Okay, perfect. So I can start sharing the screen. So let's see. Okay. Okay. Can you see the slides?
Yes.
Okay. Okay. So thank you, Paolo, for this opportunity to give a seminar in your fantastic course on analytical techniques for wave propagation. As Paolo said, this seminar will be about the generation of localized waves at microwave frequencies through leaky waves. So probably during the course you got familiar with different kinds of wave propagation. Here we see these two special classes of waves, localized waves and leaky waves, and how they can interact each other to produce very nice electromagnetic phenomena. So in this seminar, we will start with a brief introduction about what localized waves are and which kinds of localized waves can be generated in different frequency ranges. And then we will focus on two specific types of localized waves, Bessel beams and X waves, and in particular their generation through leaky waves, as I said. And finally, I will draw the conclusion. So let's start from diffraction, that is the main phenomenon underlying this seminar, because localized waves are actually a class of wave solutions that are capable of resisting diffraction for several wavelengths of distance. Indeed, as you should know, diffraction is always present and affects any kind of wave propagation. And this is something that is implicitly stated in the Huygens-Fresnel principle, that each point of a wavefront behaves as a source of spherical waves. In this seminar, we will try to answer some fundamental questions. In particular, we will see if it is really possible to beat the non-diffractive limit, if it is possible to focus electromagnetic energy in arbitrary small regions, and how we can do that at microwave frequencies. So first fundamental question is then if we can in principle really be able to avoid the spatial spreading of waves that is caused by diffraction. And one of the first answers to this question was given by Julius Andrew Stratton in the 40s, when he predicted the existence of a kind of ideal solutions, namely Bessel beams, of the Helmholtz equation that in principle do not undergo diffractive spreading as they propagate. Later, in the 80s approximately, it was recognized that a wider class of solutions to the Helmholtz equation possess non-diffractive features. And this class of waves, commonly known as localized waves or non-diffractive waves even, and they can mainly be distinguished in two classes: monochromatic solutions, then the most familiar kind of monochromatic solution is also known as Bessel beams, as we will see in this seminar, and polychromatic solutions, the most known type are probably X waves. And in this seminar, we will focus on these two kinds of localized waves, although there exist many other kinds of such localized solutions to the Helmholtz equation. At this point, we may ask ourselves why it should be interesting to focus energy in the microwave range, because we know that focusing can of course be applied even at higher frequency range, like in the optical range where laser beams solutions are actually currently employed. So when the frequency is lower than the optical range, as at microwave frequencies, the application of focused beams can be of great interest in areas such as that of 5G wireless communication or wireless power transfer, because in this frequency range it is possible to improve the focusing and reduce the interference between different among different communication channels. Another area of interest for the application of focused radiation of parameter frequencies is that of security screening and medical imaging, because with respect to the optical solution, it is easier to go more in depth in the tissue because of the larger character of the wavelength, and it also helps to avoid the ionizing character of optical frequencies or higher frequencies than the visible range. Another area of interest is that of thermal ablation because of the resonance of the dipoles of water, and in that context it is also important to focus energy in small region to avoid to warm up the neighboring tissues of a cell. So now let's move to the theoretical part of the seminar, and let's start from the definition of localized waves, starting from the wave equation in the time domain. So here is the homogeneous wave equation in time domain, and if we translate this equation in a cylindrical reference frame, we get this very well-known equation. Now, the application of the Fourier method allows us to represent a generic solution to this equation in terms of an arbitrary spectrum that is here represented as this psi function with a tilde on top. And basically, this generic solution to the wave equation in a cylindrical reference frame is represented in terms of three type of transform: two Fourier transform, one with respect to the angular frequency, one with respect to the longitudinal wave number or the vertical wave number, and the Henkel transform in terms of the radial wave number. If we now assume that for simplicity, that our system is axially symmetric, we can skip the integration with respect to the phi variable, and the equation, the previous equation can simplify as shown below, where now we also have a Bessel function of zeroth order instead of an nth order Bessel function. Now we can further simplify this integral relation by exploiting the separation relation between the vertical and the radial wave number. And also, since we are interested in the radiating region, we can limit our external integration in the radiating regime. If we apply all these assumptions to the previous integral relation, we get this simpler expression that is now just a generic integral relation that expresses a solution of the wave equation in a cylindrical reference frame that has no localized character in itself. The way we can get a localized solution from any solution to the wave equation in cylindrical reference frame depends on the property of the spectrum that is named here as S. This term here is an arbitrary spectrum, and we will see in the following slides what relation should satisfy this arbitrary spectrum in order to get a localized solution to the wave equation. First, let's see some common kind of spectra that are very well known in the literature. For example, Gaussian spectra. The Gaussian beam, for example, that is a monochromatic solution in the paraxial limit of the wave equation, is obtained for the choice of this spectrum, where you can see that the monochromatic character is enforced by this delta Dirac function, whereas the Gaussian nature of the spatial spectrum is highlighted by the Gaussian character of the term that depends on the radial wave number. If we enforce this arbitrary spectrum in this equation, we can get a closed form expression for the psi function that we will see in a while. For the Gaussian pulse, that is the polychromatic version of the Gaussian beam, we also assume that the frequency spectrum also has a Gaussian shape, as is shown here with this orange color. So instead of having a delta Dirac function with respect to the frequency, we now have a Gaussian envelope. So if we replace these two spectra in the general solution and we assume the Gaussian beam and the pulse are obtained under the paraxial approximation, we get this closed form expression for the generic solution of the wave equation that represents indeed the Gaussian beam and the Gaussian pulse. Both expressions reveal that these beams and these pulses are diffractive and dispersive. And the reason why these solutions are both diffractive and dispersive is because there is no coupling between the longitudinal wave number and the frequency. Indeed, as you can infer from the expression above of the spectrum in terms of the radial wave number and the frequency, the dependence between the radial wave number and the frequency is in both cases factorized in one function that only depends on the radial wave number and one other function that only depends on the angular frequency. Anytime you can factorize the spectrum in these two terms, you will always get diffractive and dispersive solutions. So the only way to get a localized solution is to enforce a coupling between the radial wave number and the frequency. Why it is important to enforce such linear coupling? Well, the reason for one way to understand why it is necessary to enforce a coupling between the radial wave number and the frequency to get a localized solution is by looking within the definition of a localized solution of the wave equation. Indeed, a localized solution for us is one for which the solution at a given point in space and time, z and t, recovers itself after a rigid translation over the z-axis and after a time that is proportional to the velocity at which this wave propagates. If we now apply the Fourier transform to both sides of this relation that implies the localized character of a solution, we obtain that in order to get this identity, the following constraint has to be satisfied. That implies, of course, a linear coupling between the longitudinal wave number and the frequency, or in the very same manner, a linear coupling between the radial wave number and the angular frequency. So, in order to get a localized solution, we have to enforce such a spectral coupling, and we will see in the next slides some kinds of localized beams and pulses that respect this coupling between the wave number and the frequency. So the first kind of beam that has a linear coupling between the radial wave number and the frequency is the Bessel beam. Since it is a monochromatic beam, we will have a delta Dirac function that for the dependence with respect to the frequency that enforces the monochromatic character of the solution. And then we have this other delta function that enforces that the only acceptable value for the radial wave number is that is equal to K naught times sine theta 0, where this angle here, theta 0, is called the hexagon angle. In other ways, we are actually asking to our solution to be constituted by a spectral superposition of plane waves with wave numbers that lie on the surface of a cone with an hexagon angle that is actually this theta 0, theta naught. So if we enforce this spectrum inside the general integral relation of the Helmholtz equation, we get this closed form expression that represents actually a propagating Bessel beam with an hexagon angle theta naught. If we look at the modulus of this expression, we see that this solution is actually invariant with respect to translation over the vertical coordinate. This can be better seen from this picture on the right that shows that as the z-axis, that is the vertical axis, go ahead, the transverse shape of the beam is almost unchanged. Indeed, if we look at the transverse plane at any distance from the aperture plane, we always get the same transverse shape. And that means that our solution is actually propagation invariant, or in other words, localized over a large distance. So this is in principle true even for an infinite distance, provided the aperture is infinite. But this is actually not possible on a physical basis, because the aperture that will radiate will always be finite. And the consequence of this aperture truncation is a limitation on the maximum non-diffractive distance that can be achieved. This can be explained with a simple ray optics interpretation. Indeed, if we have an aperture that emits a spectrum of plane waves with wave numbers lying on the surface of a coin, each point from the aperture will emit rays towards the axis of symmetry of this radiating aperture. And if the aperture is infinite, these rays will continue to focus the energy to the axis of symmetry up to an infinite distance. If the aperture is truncated, the last emitting rays from the aperture will focus at this point that can be easily predicted from a geometrical optics interpretation. And this defines the so-called non-diffractive distance that is given by this simple expression. So the maximum non-diffractive distance of a Bessel beam is dictated by the aperture radius of the radiating aperture times the cotangent theta naught. Other properties of the Bessel, another interesting feature of Bessel beams is that it has a focus central beam, and the transverse size of the beam is also directly related to the hexagon angle through this expression. If one has a look at these two different expressions, a trade-off immediately pops up. That is that as long as the hexagon angle decreases, the Bessel beam can achieve farther distances, but at the expense of the transverse size that will increase as well. Now, let's see how Bessel beam can be generated from a realistic device. Actually, there exist two classes of devices that can generate Bessel beams at microwave frequencies. Here we are mainly interested in planar devices. So one way to get Bessel beams is by means of a resonant aperture. In this case, you can imagine a planar structure that is fed from the center by a source and is limited on the radial axis with a circular metallic rim. In this case, we can, if we excite the structure from the center, we will have an outward cylindrical wave that will emit rays outward from the center. So in this case, we will never be able to get a focused radiation from such a structure. But since we have a metallic rim at the radial edge, if these rays are not attenuated along or are weakly attenuated along the aperture, there will exist a reflected cylindrical wave that has now an inward character. And if we recall the features of Henkel waves, we know that an inward wave will recover an outward wave as it crosses the caustic, that is here the axis of symmetry. So if we consider the interference between these inward and outward waves, we will get a stationary solution in a triangular shaped region that will define the Bessel beam solution over this triangular shaped region. On the other hand, another way to get a Bessel beam is by using a traveling wave aperture distribution. In this case, we need to have an inward cylindrical wave directly imposed on the aperture distribution. In such cases, and we will see how we can be able to have an inward aperture distribution in a realistic device. In this case, if we consider that the rays emit towards the center their energy, we will see that after the caustic is crossed, the inward wave, again, it will turn in an outward wave on the other region, and as a consequence, it will define a diamond-shaped region where the two kind of rays constructively interfere each other and creates a stationary Bessel-like solution. So these are basically the two-way, the main mechanisms to get a Bessel beam from a planar device, a resonant kind of devices and a traveling wave aperture kind of devices. I prefer to skip this slide in order not to run out of time. So I think I can first mention the historical development of Bessel beams, just to give you an idea of the various kinds of devices that have been proposed during the years. Basically, the first realization of a Bessel beam occurred in the optical range with this device that is shown in the bottom left corner, that is an annular slit in a metallic plate. And this was the first experimental evidence of Bessel beam generation at optical frequencies. And however, this kind of device was actually poorly efficient, because most of the radiation that were coming from the back of the plate were blocked by this metallic plate. So the useful area of the aperture that was used to generate a Bessel beam was quite small. In order to get a more efficient way to create a Bessel beam, hexagon lenses, as those shown here, were then proposed in the early 90s. And only after about 20 years, the first realization of Bessel beams appeared in the microwave range, and they were both based on a leaky wave mechanisms that I will explain in the next slide. Basically, the first one was proposed in 2012 by Mauret-Torre, Scott Rudolph, and Anthony Gerbich, and was based on a leaky radial waveguide operating at 10 gigahertz. And then myself, together with other colleagues, and thanks to the supervision of Mauret-Torre, that was one of the main inventors of the previous device, were able to generate Bessel beams at millimeter wave frequencies by using a similar device that were based on a different kind of leaky wave mechanism. Okay, so let's move to the generation of Bessel beams through leaky waves. So in the previous explanation of the generation of Bessel beams through a classical ray optics interpretation, I have tacitly assumed that all rays shared the same intensity, and this implied that the wave number was always a real quantity. But if the ray is attenuated along the radial direction, we should use a complex wave number that in this case we call a complex leaky wave number that is characterized both by a phase constant and an attenuation constant, also called leakage rate. How this affect the generation of Bessel beam? Well, in principle, we can think that this complex ray is just but a ray with a complex weight that basically explains the attenuation of the ray along the radial direction. As a consequence, each ray will have a decreasing power that reach the axis of symmetry of the structure. And as a consequence, the non-diffractive range might be affected by the different power that is carried out by each ray. And as a consequence, it will be reduced of a quantity that is in some way proportional to the leakage rate of that characterize the wave number that is propagating in the structure. However, if such a leakage rate is sufficiently small, a Bessel beam is still generated. Here you see two examples. In this case, you see that the attenuation constant or leakage rate is just 0.005. The vacuum wave number is very small. And indeed, as you can see, the Bessel beam reaches with almost the same intensity the non-diffractive range predicted by ray optics that is here emphasized by these white dashed lines. You can see that the higher tip of this triangular region that is predicted by classical ray optics for real wave numbers is reached by the intensity of the Bessel beam. When the attenuation constant is lower, for example 0.02, the Bessel beam is still generated, but now you can see that the Bessel beam doesn't reach the non-diffractive range that is predicted by classical ray optics, but instead reaches a shorter distance that can be predicted by this formula here reported above. Moreover, we can do more when we have a leaky wave number, because we can also think that we have the degree of freedom of modulating this leakage rate along the radial direction to create a sort of arbitrary envelope of the weight of this ray of these rays along the aperture along the radiating aperture. This kind of possibility opens to a lot of possibilities. One is to modulate the attenuation constant along the radial direction to get a Gaussian envelope, and then to realize the so-called Bessel ghost beams. This is just one possibility that I wanted to mention, but we will not see that in this seminar. Now, I want to show you some practical realization of devices at microwave frequencies that are capable of generating Bessel beams, and give you just some ideas of how they can be designed. For example, here you see the leaky radial waveguide that was first studied by Mauro et Torre and later by myself. And you can see that this structure is basically a resonant cavity that is half a wavelength thick and is just a few wavelengths large in the radial direction, that is fed from the center with a coaxial probe. As explained in the previous slide, this is a sort of resonant launcher that will create a Bessel beam in a triangular shaped region. In order to get radiation from this device, we have to cover this cavity with a partially reflecting sheet that can be at the first approximation represented by an equivalent surface impedance. If we analyze this device, if we analyze the one-dimensional section of this device, we can also get a simple equivalent circuit model of the structure that is reported here on the right, that can be easily solved through the application of the transverse resonance technique that gives a dispersion equation for this transverse equivalent network. So the roots of this dispersion equation will give the transverse resonances of the structure, and in particular the leaky modes that will propagate in the structure. Here you see that one of the leaky wave solution of this dispersion equation is represented here in the figure below as dotted blue lines in a range that goes from few gigahertz to 5 gigahertz. On the other hand, since the structure is also resonant along the radial direction, because it is a cavity that is a few wavelengths long along the radial direction, we also have an equation for the radial resonances of the structure that are basically given by this dispersion equation that correspond to finding the zeros of the zeroth order Bessel function. So the radial resonances of this device corresponds to the radial wave numbers that resonate with one of the zeros of the Bessel function that are here highlighted with this key sub 0n as a symbol. And in this figure here, you can see the first three radial resonances reported in red, brown, and magenta. So if we look at this dispersion diagram on the right, we understand that the leaky mode that has been found by solving the dispersion equation for the transverse network will resonate at these three different frequencies with the first, the second, and the third zero of the Bessel function. Now we can find some design equation to realize such launcher to work at a given frequency. For example, we can ask ourselves that we want a device that is capable of resonating with 5 zeros of the Bessel function with an aperture radius of a given dimension, with a wave number that is fixed a priori by ourselves at a given frequency. We can find the design equation for finding the cavity height and the surface, the sheet impedance of the partially reflecting sheet that is put on top of the cavity to allow for radiation. And this design equation that are here not shown, two values that are the, let's say, optimum values to have a leaky wave that generate a Bessel beam with the features described in the box shown on the left. Then we need to synthesize a partially reflecting sheet that exhibit this value of the sheet impedance, and this can be done with standard techniques. For example, array of patches give a lot of array of patches of sub-wavelength character gives a lot of degrees of freedom to design such surface impedances. And once we do that, we can again find the dispersion equation for the leaky mode that propagates in the structure with the prescribed radial wave number, and also evaluate the radial resonances of the structure for the fixed aperture radius. So as the dispersion diagram on the right shows, the resonances of this leaky mode are supposed to occur here at about 37 frequencies with 37 gigahertz with the fourth zero of the Bessel function, at 39.6 gigahertz as predicted by our design equation with the fifth zero of the Bessel function, and again at more than 40 gigahertz with the 60 of the Bessel function. However, in such a structure, also surface wave will propagate and will resonate with the radial resonances of the structure. In particular, we will have the TM, transverse magnetic surface wave, of the structure that will have this dispersion curve that will resonate with the 9th zero of the Bessel function at about 40 gigahertz. These resonances can be seen and observed by full wave simulations that are obtained with the COMSOL multiphysics that are reported here. Here you can see a video that shows how the near field distribution changes for different frequencies. Here you can see that at 37 gigahertz we have the first resonance with the fourth null. When we approach the 39.6 gigahertz, we have a resonance with 5 zeros of the Bessel function, and now we will have a surface wave contribution up here with 9 zeros. And this shows how this structure is supposed to resonate with both leaky waves and surface waves. This structure has been actually fabricated at the University of Rennes, where I have a long-standing collaboration with Professor Mauro Torre and Ronan Solo, and has been actually measured and validated at 40 gigahertz in the near field test range that was available at that university. Okay, now let's move to the second part of the seminar that covers the generation of X waves that are basically the time domain version of Bessel beams. So first, I will comment some of the theoretical. I will provide a theoretical framework to understand how these X waves work, and then as I did for the Bessel beam, for Bessel beams, I will show you how leaky waves can generate such X wave solutions. So by definition, an X wave differs from a Bessel beam just for having a polychromatic frequency spectrum in the choice of the spatial and frequency spectrum. As a consequence, instead of having a delta Dirac function that implies that the frequency is fixed at a given that the frequency is fixed, we will have a generic arbitrary frequency spectrum. Depending on the shape of this arbitrary frequency spectrum, we have different kind of X-shaped pulses. This is the way we call a Bessel, a polychromatic version of a Bessel beam. When this arbitrary frequency spectrum has the expression reported here in this box, this is actually the correct definition of the ordinary X wave. However, as you can see, this solution defines intrinsically a low frequency spectrum, but X waves are straightforwardly generalized to high frequency spectrum by frequency shifting, for example. So in the literature, for a sort of synecdoche, X-shaped pulses are commonly referred to as X waves, regardless of the type of frequency spectrum. In the following, for simplicity, we will assume that this frequency spectrum is just a rectangular function centered at the working frequency. One of the interesting aspects, one of the remarkable features of X waves is that they not only show a focused character along the transverse plane, but also on the longitudinal plane. And this is actually a consequence of their definition. Indeed, for a uniform frequency spectrum, that is when, as I said, we assume that the frequency spectrum is uniform over a given bandwidth, that is a rectangular function centered at the working frequency. the definition of an X-waves is just a Fourier transform of the Bessel beam. So since the propagation of an X-waves occurs along the vertical z-axis, the larger will be the bandwidth over which this polychromatic solution is generated, the narrower will be the size of the pulse along the longitudinal direction. Instead, the transverse resolution of such pulse will be inherited by the Bessel beam solution. So basically, we will have that the only difference between a Bessel beam and an X-wave is the confinement along the longitudinal propagation direction. Basically, on the transverse sides, the resolution of an X-wave is the same of the Bessel beam if they are generated with the same hexagon angle. Along the longitudinal axis, the propagation axis, the transverse sides of an X-wave will be inversely proportional to the fractional bandwidth that is used to generate such a solution. At this point, it is interesting to define some metric of confinement for X-waves to understand how much they are confined along the both the radial direction and the vertical direction. To this purpose, we define this metric. We have an area of an energy confinement defined along the radial axis and the propagation direction, that is the z-axis. And we can see that we are interested in focusing the energy over an area that is as large as the aperture diameter, of course, of our radiating aperture, and over a distance that is limited by the non-diffractive range, because the non-diffractive range of an X-wave will also be the same of a Bessel beam. So the pulse will travel with almost the same intensity up to the non-diffractive range, and then it will abruptly vanish. So we are interested in having a small longitudinal sites only up to the non-diffractive range. So basically, we can define that the main energy of our pulse will be measured with respect to the non-diffractive range for the longitudinal sides and with respect to the aperture diameter for the radial sides. Basically, we have these two confinement ratios that are called 0 for the transverse sides, that are the ratio between the radial spot sides and the aperture diameter, and the longitudinal confinement, that will be the ratio between these longitudinal spot sides and the non-diffractive range. If we now combine these two confinement ratios, and we say that our pulse will be confined only when both the confinement ratio and the confinement ratio along the radial and the longitudinal direction are smaller than 1, we will get this nice figure reported here that reports this metric of confinement as a function of the radial, the aperture radius along the x-axis and the hexagon angle over the y-axis. So the way this figure has to be interpreted is the following. When you see a dark area, it means that the pulse will never be confined along both the radial and the longitudinal direction if the aperture radius and the hexagon angle that have been fixed to design such device are in this dark area. If you look at the light area, this is the allowed range of values for the hexagon angle and the aperture radius, where you can get a pulse that is actually confined along both the longitudinal and the radial axis. Here you can see some equation that defines these boundaries that are not important to get here a first interpretation of the phenomena. But this slide instead gives you a clear understanding of this figure. For example, Here you see that if you choose the aperture radius to be about 25 lambda wavelength, the lambda is the wavelength at the working frequency, and the exciton angle is about 20 degrees, the pulse will have this nice confined shape along both the propagation direction and the radial direction. If you change the point and you move this operating condition where P2 is displayed, you see that the color is not as lighter as before, and as a consequence, the pulse will start to broaden a little bit, in this case along the radial direction. Here, if we place our working conditioner below in this dark area, we will see that the pulse will be confined only along the transverse direction, but not in the longitude. In this small region here, it happens the opposite. That means the pulse is confined along the longitudinal direction, but not in the radial direction. And finally, here in this small region, dark region here, we see a case where the pulse is not supposed to be confined neither in the radial or the longitudinal direction. So these results have been obtained by assuming a fractional bandwidth of 20%, but as I said, the fractional bandwidth has a key role in determining the confinement along the longitudinal axis, that is the axis of propagation. Indeed, if we assume the fractional bandwidth to be as low as 1%, this will be almost equivalent to a Bessel beam, because a Bessel beam has no fractional bandwidth, has 0% fractional bandwidth. And indeed, a pulse generated with a fractional bandwidth of 1%, as shown here, recovers basically a Bessel beam that is propagation invariant and not confined along the propagation direction. But if we now increase the fractional bandwidth, we see that the pulse will start to squeeze along the longitudinal direction. And we can see that as the fractional bandwidth is larger than about 20%, the pulse is very well confined and doesn't increase the confinement much. So this gives us a rule of thumb to determining what is the required fractional bandwidth for a microwave device to generate a pulse that is actually confined. So, of course, these evaluations and calculation are based on ideal assumptions that the X wave is non-dispersive, but over a large frequency bandwidth, this is no longer true, because the exciton angle will change with the frequency. However, if the frequency dispersion of the exciton angle, that is called also cone dispersion, along the fractional bandwidth is not really important, we are still able to generate a limited dispersive X waves. So you can find some rigorous explanation on this phenomenon on some references that I provide at the end of the seminar. Anyway, it is good to have an idea of how the experimental validation of X waves went along in the history. And basically, the first realization of X waves appeared only in the early 90s in acoustics, and were followed after 10 years in the optical range, basically. But in order to have an experimental validation of X waves at microwave frequency, we had to wait up to the last few years. The first experimental generation was proposed by Nicolaus Chiotellis and under the supervision of Professor Gerbich in Michigan, University of Michigan, in 2018. And then we have been able, together with a colleague of mine, Davide Comite, that is here in Sapienza University, to provide an experimental validation at microwave frequency by means of a leaky wave antenna almost in the same year after a few months. So In order to conclude this seminar, I want to show you how we can generate indeed these interesting X-wave solutions with leaky waves. And one possibility is to use leaky periodic radial waveguides, because as I shown at the beginning of this seminar, we have two ways to generate Bessel beams. One distribution. The resonant kind is intrinsically a narrow bandwidth device, and so is not suitable for generating F-waves. Instead, if we can use traveling wave devices, we are in principle capable of obtaining a Bessel beam over a wide frequency bandwidth, and so in principle we could be able to generate an X-waves. This is indeed possible by using, for example, a leaky periodic radial waveguide that can, due to the radially periodic nature of the structure, can be the leaky mode that is propagating in the structure can be described in terms of the usual Floquet block theory, and so the radial wave number that propagates in the structure, it can be obtained by this Floquet block expansion. So each harmonic that propagates inside the structure can be described by a radial wave number that is provided by the expression below. We can design the structure in order to have just the -1 Floquet harmonic propagating in the structure, and this is essential in order to have at a given frequency the phase constant of the radial wave number negative in order to have a backward leaky wave. This is extremely important for our purposes because we need, as I have shown in the first slides, an inward ray that is emitted from the structure. And since we have a source that emits rays in the outward direction, we need a negative phase constant to have backward radiation. If we design the structure, as I said, in order to have at a given frequency a phase constant, a normalized phase constant that is in the radiating regime, that means that has a normalized phase constant that is lower than 1, and a negative value of such a phase constant, we are actually able to have rays that are emitted towards the center of the structure, and as a consequence, focused Bessel beams. We can design the structure by using approximate equation to have an approximate expression for the dispersion curve of such periodic structure. So basically we can assume that the background mode of the structure is just a slight perturbation of the parallel plate waveguide mode that propagates in the structure, and by means of this assumption we can be able to have a design equation for the period of the slots. Another thing that we can do to find the design equation for the structure is to determine the dielectric constant that is needed in order to have a low dispersion of the mode over a given frequency bandwidth. And finally, we can cite the slots, the width of the slots that are etched on this aperture in order to have a leakage rate that is not too high to prevent the formation of a Bessel beam for the reasons that I explained at the beginning of the seminar. At the end of the story, we find that a good trade-off for having a good X-wave or a good generation of Bessel beams over a wide frequency range is given by the criterion reported in the right bottom corner. Well, now that we obtain this approximate design equation for this structure, we can see if we have been really able to generate an X wave from a leaky periodic radial waveguide. For example, you can see here that for these design parameters, we found some design equation that allowed us to operate at this point in this chart reported here, that ensure that basically the X wave will be highly confined in both the longitudinal and the radial direction. If we look at the dispersion diagram and the generation of the Bessel beam over a fractional bandwidth of 20%, we get the near field distribution that are reported below. You see that as the frequency increases, the non-diffractive range increases, and this means that actually the excicon angle is not really the same. There is some dispersion, but is acceptable for having a pulse that is still confined and not much dispersive. This can be seen if we look at the time domain version of the X waves that shows actually a very well confined pulse that maintains its shape as the non-diffractive range is reached. After the non-diffractive, beyond the non-diffractive range, you see that the pulse is starting to vanish. So this device has been actually fabricated and measured, and actually we have been able to obtain a pulse that is confined when generated with a fractional bandwidth of 10 and 20%. Here you can see the time evolution of the pulse. Actually, the measurements were not as good as the simulation because of the fabrication tolerances, but we were quite satisfied because it was one of the first experimental validation of such solutions in the microwave range. So to conclude my seminar, I hope you enjoyed this topic. I started by from a very general physical phenomenon that is diffraction, and commented the possibility to beat such a diffraction limit that affect any kind of wave propagation by looking at some peculiar solution that can resist diffraction over considerably large distances. We have seen that Gaussian beams, although they are quite focused, they are diffractive and dispersive beams, and this is a consequence of the factorized character of the spectrum over which they are generated. If we enforce instead a linear coupling between the radial wave number or vertical wave number and the frequency, we can get an entire family of localized waves that in this seminar we have discussed just two kinds of them, Bessel beams and X waves, and in particular their generation at microwave frequencies by using leaky waves that are complex solutions of the wave equation. So I hope you enjoyed this seminar, and I conclude my talk. So here you can see a list of references that are pertinent to the topics that are covered in this talk. And if you have any questions, I'm here to reply to your comments. Thank you.
Thank you very much, Walter, for your beautiful seminar. I'm sure you have enjoyed it. This is actually an extremely interesting area of research, a hot topic of the last decade, and presumably will remain such a hot topic also in the next few years. So if you have any questions, please ask them. I would like only to add that I will post a PDF version of these slides on the e-learning website in the near future. Okay, so if there are no questions, I would like again to thank you for your attention and for attending this course. Should you have any question about the content of the course as well as of the seminar, you can write to me or directly to Dr. Fuscaldo. And as I was also mentioning in one of the last lessons, in order to formally pass the examination associated with this course, the idea is to prepare one topic that is one of the lessons I gave, and we can arrange for an oral exposition whenever you feel you are ready for doing that. Okay, so thank you again very much, and see you soon, all.
Grazie,
Bye.
grazie, arrivederci.
Bye.
Thank you. Bye.
you.